Hey everyone, we're about to jump into something pretty wild. It's this fundamental clash right at the heart of science, how two of our most powerful ways of seeing the world, chemistry and quantum physics, can look at the exact same thing and see two completely different realities.
So let's start with a question that sounds, almost laughably simple. What is a water molecule, right? We all learned it in school, H2O. But it turns out the real answer completely depends on who you ask.
So is it just a collection of little parts, kind of like a tiny construction set? You've got two hydrogens snapped onto an oxygen? Or is it something else entirely? A single, unified, indivisible system where the very idea of parts just doesn't really make sense anymore? This right here is the core conflict we're going to dig into.
Okay, first up, let's put on our chemist goggles. For a chemist, the world is all about these tangible, connected parts. And honestly, this approach feels really intuitive, mostly because it's how we're all taught to see the world from day one.
The absolute best way to think about this is Legos. Seriously, atoms are like Lego bricks. You've got your red brick for oxygen, a couple of white ones for hydrogen, you snap them together, and poof, you have a water molecule. But here's the key. Even when they're connected, they're still individual bricks. They each hold on to their own identity.
And this whole viewpoint has a super practical purpose. I mean, the chemist's job is to classify millions of different substances. To even start doing that, they have to know the structure, literally who is bonded to whom, because that structure is what lets them predict how a molecule is going to react. They care about how an atom behaves in situ, in the specific environment of that molecule, because a hydrogen atom in water isn't quite the same as a hydrogen atom just floating around by itself.
All right, deep breath. Let's switch gears completely. We're now entering the world of the quantum physicist. And this is a world where our everyday intuition about parts and wholes, it just starts to completely fall apart.
So, if the chemist's molecule is like Legos, the quantum physicist's molecule is like a smoothie. Think about it. You toss a banana, some strawberries, and maybe some yogurt into a blender. You hit the on switch, and now where's the banana? Where are the strawberries? They're gone. They've totally merged into this single, indivisible new thing. They've lost their original identities and just become part of this holistic, smoothie. And here's the kicker. The physicist isn't trying to classify things based on their structure. Their main goal is to calculate the energy of the entire system. From their point of view, those individual atoms, the parts, are really just a mathematical convenience. They're a useful place to start your calculations, but they aren't actually real in the final molecule. The molecule is just one global interconnected entity. Okay, so we've got two very different models, Legos and smoothies. But where do they actually run into each other? Well, it happens when you look at stuff like isomers and chemical reactions. That's where these two worldviews lead to totally different conclusions. Let's take a look at the chemical formula C2H6O. Now, to you and me, that just looks like one specific mix of atoms. But if you show that to a chemist, they'll tell you it's a recipe that can make two completely different things. And this slide just lays out the divide perfectly. On the left, the chemist sees two totally separate molecules. Ethanol, the alcohol in drinks, and dimethyl ether, which is a toxic gas. Different structures, different properties, different things. But the physicist, they just see one C2H6O system. And on the energy map for that system, there happen to be two stable valleys that we experience as those structures. They aren't different things, they're just different stable states of the same thing.
Now let's zoom in on that ethanol molecule. To a chemist, that one single hydrogen atom stuck to the oxygen, it's everything. It's what's known as a functional group, and it's the reason ethanol is an alcohol. That one atom is special. But to the quantum physicist, nope. All 6 hydrogen atoms in that system are fundamentally, completely, 100% indistinguishable from each other. You literally can't label one as special because they're all just identical parts of that quantum smoothie.
This whole conflict gets even sharper when we talk about a chemical reaction. The chemist wants to figure out the mechanism. They want a story, a step-by-step narrative. First this bond breaks, then this atom scoots over here, and then a new bond forms. It's a movie plot. The physicists, though, they create a map of the potential energy surface, which is like a bird's eye view of every possible arrangement of those atoms and how much energy each arrangement has.
And here's what that map looks like. For a physicist, a reaction is really a journey. You start out in a low-energy valley. That's your stable ingredients, your reactants. And to get to the products, which is just another stable valley, you have to travel up and over an energy mountain. The path your system takes across this landscape is the reaction.
And that highest point on the mountain pass, that moment of max energy and instability, that's called the transition state. You can think of it as the point of no return.
Once the system gets over this hump, it's just going to naturally roll down the other side into the product valley. It's this beautiful, holistic picture of the entire process.
Okay, so we've got Legos versus smoothies. We've got stories versus maps. Why does this fundamental difference in how we see things matter so much? Well, it gets right to the heart of why quantum mechanics is so hard to wrap your head around. And at this point, I'm sure you're asking the most obvious question, right? Which one is actually right? Is it the chemist or is it the physicist?
And the answer is, well, they both are. They're both incredibly powerful and totally essential models. They're just designed to answer very different kinds of questions. A chemist needs a model to help them sort and predict the behavior of millions of compounds. A physicist needs a model that can calculate the basic energy states of a system from the ground up. The reason quantum mechanics feels so profoundly strange is because it asks us to completely let go of that first model, the one that feels so much more intuitive to us.
So here's the bottom line. Our entire lives, and especially our early science classes, have trained our brains to think like chemists. We see the world as being made of distinct parts, of building blocks. And then quantum mechanics just waltzes in and tells us that on the most fundamental level, that whole intuition is wrong. It literally asks us to unlearn one of the most basic ways we have of making sense of reality.
Now, the source material actually suggests there might be a better way to teach this, to kind of bridge that massive conceptual gap. Instead of just throwing people into the deep end of the weirdness, maybe we should follow the historical path. You start with those old-school classical solar system models of the atom. Then you introduce Niels Bohr's game-changing idea that those orbits can only exist at very specific, quantized energy levels. And only then, once that idea of quantized is sunk in, do you introduce wave-particle duality. It creates this logical ladder that slowly leads you to the modern, super strange concept of the orbital.
Because ultimately, the author argues, the goal of teaching science isn't just to fill students' heads with a bunch of facts and pictures of molecules, like some kind of mental catalog.
No, the true goal is to build a genuine understanding of the molecular world and all of its complexities. And that means understanding not just what a molecule is, but also understanding the different, powerful, and sometimes conflicting ways we figured out how to describe it.
And that kind of leaves us with a final big thought to chew on. We've been talking about molecules this whole time, but what if this isn't just about physics and chemistry? What if other things we're so used to seeing as simple collections of building blocks, our societies, our economies, maybe even our own consciousness, are actually more like those quantum smoothies? Inseparable, holistic systems where the whole isn't just greater than the sum of its parts, but fundamentally different from them. What changes when we start looking at the world that way?